Hi, welcome to a brand new episode on generative AI. My name is Satyajit Pattnaik and I welcome you all to my channel. In case you are a complete beginner in the field of generative AI, I already have a 6 hours dedicated video on generative AI for you to get started learning about generative AI concepts like RAGs and multiple other topics. I would encourage you to explore that video. The link will be in the description. Now, the purpose of this video is going to talk about some advanced topics, something related to LoRA, QLoRA and quantization. This could also serve as a part 2 of that particular video. Now, before jumping into this video, I would also like to tell that when I started learning about fine-tuning like 1 year back, I was taking reference from multiple platforms, multiple videos. I went through multiple YouTube videos, blogs. I went through multiple courses, multiple resources, research papers, and one thing that I understood was it's very difficult to understand some of the topics like LoRA, QLoRA, quantization, fine-tuning, when to use fine-tuning, when to use RAG-based approach, and unless and until you actually work on the ground level, you will not be able to identify the actual differences. I went through multiple videos and I was not clear on these topics, to be very honest. I was struggling to understand. And when I was struggling to understand, I also thought that if I am struggling, my students will also be struggling, right? And that's where I took idea from multiple videos, from multiple research papers, and here we are talking about this topic. And I'm pretty much sure that this is going to be one-stop solution to you. In case you have any doubts around this topic, the title of which you already know, I'm pretty much sure that your doubts will 100% be clear on LoRA, QLoRA, quantization, when to use fine-tuning and all these kind of questions. Now, if you are a complete beginner into AI, you want to get into data science, AI, machine learning, generative AI, I also have a dedicated data science and AI master's program that you all know. It's available on Udemy, available on my platform, and people who follow me, they know what's the difference between Udemy and on my platform. I provide 24/7 support with resume preparation and interview preparation on my platform. On Udemy, the support is very minimal because if you pay 400, I get around 150, 160 from Udemy. So it's difficult for me to give time to my Udemy students, but still I give them time. But on my platform, of course, my students are my top priority. I will also have my WhatsApp number in the description in case you want to get connect with me. Let me know. Apart from that, let's get started with the video. I'm sure you will love this. This is a very I would say advanced topic. In case you are a complete beginner, recommend you to go through my other 6 hours of videos and come back to this one. And in case you have any other requests, any project demand, anything, you know where to go. Comment down below and I will reach out to you. That's it. See you in the video. Enjoy. Hi, welcome back. In the next set of videos, we shall be focusing on fine-tuning, and that is with respect to large language models. Now, when it comes to machine learning, deep learning, or even generative AI, there are majorly two approaches that we usually discuss. One of them being pre-training, and one of them being fine-tuning. Let's try to understand what each of them means. Pre-training is nothing but the initial phase where a model learns from a large data. Let's say you have a specific model. You are giving access to a large amount of data for this model, and the model gets trained. Internally, this model is nothing but a neural network based model, right? Like generative AI is eventually nothing but a part of deep learning, right? Transformers. So a model is being trained with trillions and trillions and millions of data, right? So pre-training is basically the initial phase where the model learns from a large and diverse data without a specific task in mind. We don't have any specific task in mind, but still we want to pre-train a model so that a model can be ready. What is the purpose of this model? The goal is to build a strong foundational understanding of language, grammar, and context. For example, I'm just talking with respect to large language models, right? There are many large language models. There are language models in form of APIs, language models in form of open source, right? And all of these models, let's say when you talk about APIs, OpenAI has multiple models, right? Like GPT 3.5, GPT 4, 4.0, whatever it is. And then we have XAI, they have Grok 2, Grok 3, and so on. Open source also has a tons and tons of models like Llama, Mistral, Mixtral, many more, right? When it comes to Llama also has different variants. Let's say one of them is Llama 3.1, one of them is Llama 3.2, one of them is Llama 3.3, one of them is a tiny llama, right? Now let's take an example of tiny llama. So tiny llama, if you want to check tiny llama, you can quickly go to Ollama models. You will be able to see tiny llama. Tiny llama is also available on Hugging Face. If you simply go for Hugging Face tiny llama, you should also be able to get the link where you can download this model. This is a 1.1 billion chat model, right? 1.1 billion llama model on 3 trillion tokens, right? Now this is different and this is different. Could be, but eventually it looks same. My bad, because this is also trained on 3 trillion tokens. This is also 3. So eventually these two are both the same models, right? So if you want to use tiny llama from Hugging Face, you have to download this model. If you have to use directly from Ollama, you can just simply install Ollama on your systems. Whether it is a Mac system, Windows system, you can easily install Ollama and get started with it, right? So taking tiny llama as an example, tiny llama is nothing but a 1 billion parameters model, right? That means the internal architecture of tiny llama could also look like a complex neural network like this, and it also has a 1.1 billion parameters, or in simple terms 1.1 million weights, right? So bunch of data is also provided, and based on that the tiny llama model is ready, right? What you can do with tiny llama, you can do a lot of things, right? So this is your pre-trained model that is already trained. Now there could be a very specific case. For example, I'm working into, let's say I'm talking about a very specific domain. Let's say I'm working on an insurance domain, right? Or maybe any domain, let's say medical domain, right? So in medical domain, there could be many such jargons that is not understood by humans, right? MBBS. MBBS is a very simple word. We know the meaning of that, but I'm just telling you that there could be multiple medical terms, right, which is very difficult for us to understand, right? Now what if you want to specifically use your medical data? Let's say you are working for a medical company, let's say XYZ pharmaceutical company, right? And in this XYZ pharmaceutical company, which is a medical domain company, you have gigabytes and gigabytes of data. Let's say, just assume you have 20 GB of data, right? You want to create your own model. Let me tell you, training your own model from scratch is a very tedious process. It takes ages. It takes a lot of time to create your baseline model. But if you use an existing brain and train your own data so that the brain gets trained on your very specific data, now when a user comes in or anybody comes in and asks something related to this industry, medical industry, especially about your own data, you should be able to get some answers. And that is exactly what fine tuning is. Fine tuning, theoretical definition is, it is the subsequent process or a phase where the pre-trained model is trained further on a smaller task specific dataset. And the purpose is very simple, to adapt the model's general knowledge to perform well on a particular task. Okay, so I hope it is understood. So I already took an example of Tiny Llama, a large language model with 1.1 billion parameters. During its pre-training phase, Tiny Llama learns from vast amount of data. It could be textbooks, it could be Wikipedia pages, it could be multiple different pages and websites, and it is learning, and it has been created, right? In a simple analogy could be let me take an example. Something like, let's say you want to teach a child to understand language. It could be any language, right? Through exposure to many different stories and conversations. They learn vocabulary, then they learn how to create sentences, and then the way language works in various contexts, right? And fine tuning is basically, it's very similar to talk. Basically, you take that same child and giving them specialized resources like textbooks or on a particular topic, and help them to write essays or engage. Now, fine tuning and pre tuning are not new concepts when it comes to machine learning or deep learning, right? Let's especially talking about deep learning. In deep learning, we also have touched about these topics like pre-trained models and fine-tuning models. There are multiple pre-trained models. Let's say MobileNet, ResNet, Inception, V3, V4, V5, VGG models. There are many models that are already pre-trained on thousands and thousands of classes. Now, creating something from scratch, let's say you want to create your own neural networks from scratch, it could be very time consuming and resource consuming task. So always a better option is to use fine trained model my bad pre-trained model as your first layer, and then train your next layers to achieve your output. That means you use the brain of these pre-trained models, and then train your own layers or your own data, and then you will be able to achieve the final target. For example, you're talking about MobileNet. Now MobileNet is, let's say, trained on 1,000 classes, right? It might not be trained on your own class. Let's say you are trying to solve a problem of, let's say, X-ray images. You want to identify people are having COVID or not, right? Based on X-ray images. Now these are two different classes, class 1 and class 2. Now these two classes might not be a part of this list of 1,000 classes, fine, but still the brain MobileNet has, if you use that brain as a pre-trained model and then train your COVID data and non-COVID data, you will still be able to get some better results. And that is exactly what fine tuning does. It basically goes, fine tunes, and creates a better version of that model which solves very specific problems. Okay, now one thing might come to your mind, because you all know about RAGs, right? We have already talked about RAGs, retrieval augmented generation. One thing that might come to your mind is, how is RAG different than fine tuning? Because we already talked about RAG, right? Fine tuning sounds very similar to what RAG does. What is the difference? We will be talking about the differences of RAG and fine tuning in the next video. Hi, welcome back. In this video, we shall be talking about the differences between RAG and fine tuning. And what is RAG? I think everybody knows about RAG for now. when we when your large language model does not work well with your own data or your custom data, that is where RAG comes into picture as a superhero and tries to solve your problem. RAG tells you that you give me your custom data, I will be able to use the LLM's brain for chat completion and I will be able to solve this problem. Right? Now, for example, let's say we're talking about a very specific example. I have some AI notes or data science notes, right? And all of these notes are in PDF format. So what happens is in RAG, you basically take your data, you chunk it down, and after chunking down, the very next step is to convert each chunk into vectors, right? So it works something like this. Each chunk becomes a vector. Now all of this vector data goes and gets stored somewhere, right? So let's say the data is getting stored in a vector database, and you have a front end where a user is asking a question. Let's say something from these notes. What is the difference between supervised and unsupervised learning? There is a text. Text is also converted into vectors, the exact fashion how this works. And here you're basically going to the vector database to fetch the relevant information. In vector database, there are multiple vectors: v1, v2, v3, vn, right? Let's say this and this are your relevant information. So you basically go ahead. So input plus relevant information, and then you are calling the large language model. So large language model does not have the information about your entire nodes, right? It only has information about input plus relevant information, and then you are getting the output. LLM is basically doing the chat completion part. This is RAG, and everybody knows about this. Now what is fine tuning? Little bit different. So what happens in fine tuning? In fine tuning, let's say you have some public data, right? Or let's say you are working for your medical company and you have your medical related information. In fine tuning, let's say we have public data coming from different sources like wiki pages, various news articles, various Google articles, and various other resources. Let's say you have trillions and trillions of data, and when you are training this, you are basically getting the foundation LLM. And what are these? You can also call it as a pre-trained model. Let's say Llama or different GPT models or XCI models or Mistral or Mixtral, whatever. These are all pre-trained models. Now imagine you have this organization. I'll write it down as org, right? And let's take an example. This is a healthcare organization. Now they have gigabytes of data. And then when you are using this data on top of these pre-trained models, this is where fine tuning comes into picture. Okay. So fine tuning is done on labeled domain specific data. And then you are getting the fine tuned LLM. What you are doing here is you are taking a pre-trained model as pre-trained model itself is a concept where you're taking somebody's brain, and then on top of your own organization data, you are fine tuning it. And then you are finally getting the output. So very similar to RAG, but fine tuned LLMs or fine tuning process itself is different than what RAG is. So end goal is same. End goal of RAG and fine tuning is same, right? But fine tuning is mostly used for smaller, specialized label data set and adjusting the model parameters and embeddings based on the new data. Now, the next question is, if both are same, what is the difference between both of them? We will be talking about differences. If you ask me as a layman generative AI specialist, what we usually do is when we start working on a particular use case, we first see, can we use a foundational model like a pre-trained model to achieve something? If yes, then there is no need of RAG or fine tuning. If we are not able to achieve, then we take help of RAG. If we are able to achieve, well and good. If not, then we go ahead and try to do the fine tuning. So fine tuning is definitely the last step. If RAG fails, then only we should go ahead for fine tuning. Now there are differences or reasons behind it, because fine tuning is little bit more expensive process than RAG. RAG is an easier approach. Okay. Now, which scenario to use RAGs and when to use fine tuning, let's try to understand more into that. Hi, welcome back. Let's try to talk about when to use RAG. And after this, we will try to talk about when to use fine tuning. So for most of the use cases, as I told you, that RAG is a better fit. Okay. And fine tuning. And that is because of multiple reasons. Now, one of the reasons is more secure, more reliable, more scalable. Okay. Let's try to understand about each one of them. What do you mean by more secure? When you are using RAG, you know the architecture, I'm not going to repeat it. When you are using RAG, your data stays in a secured environment. Okay. When you're talking about more reliable, RAG delivers trustworthy results. I mean, again, that comes with experience. I have tried out multiple use cases. I have tried multiple RAG use cases. I have also done a lot of fine tuning in various client projects. With experience, I can say that RAG is more secure. Data stays in your secure environment. RAG delivers trustworthy results, right? And apart from that, it is also scalable. It is cost efficient and scalable, right? So let's say you have some data sources, and from these data sources you need to have a constant pulling. One simple example is, let's say there is a company X who wants to create a chatbot on top of their scraped information from their website, and the scraping part has to be automated so that every day we can go through the website and see whether there are new pages to it or not. So we need a constant pulling here. So I will definitely go ahead with RAG. RAG is a better approach here, um, because if anything goes wrong, data team can easily trace the source and identify where the mistake is or where the problem is and fix the problem immediately, right? So this is all about when to use RAG. Talking about when to use fine tuning. Of course, fine tuned models performance of fine tuned models are greater than performance of RAG based models. Now this is definitely true. Okay. And when do we use fine tuning? If explicitly there is an organization call, the organization needs us to use fine tuning, well and good, performance will be better. Even though it's a costly process, we have to do this. Second one will be, if response needed to detailed prompts in a niche tone or style, or maybe let's say you're dealing with legal components or you're dealing with very specific abbreviations, I'll give an example. Let's say you are dealing with medical data, and this medical data has a lot of abbreviations, lot of terminologies, and if you are just using 2 or 3 pages based on RAG architecture, your model will be able to give you answers, but it will not be able to understand the context 100%. So in this case, if you want to use a very specific data, then uh, um, fine tuning is definitely preferred, right? So it's basically a great fit for overcoming information bias and other limitations such as language repetitions or inconsistencies. Okay, so my call, how to choose between RAG and fine tuning. Let's try to wrap it up. It's a little bit difficult to understand, but it's not that difficult, right? So my first choice will always be RAG. As a generative AI specialist, whenever a client is coming to me, they want to do some sort of a automation like a chatbot or anything, then I will definitely go ahead with RAG because it is most preferred, generally better for most enterprise use cases, and also cost efficient. So if I talk about RAG features, the RAG features are cost efficient, less time consuming, easily can trace back sources and fix problems, less memory consumption, generally considered better for most use cases. What else? I would also say most preferred. Okay, now talking about fine tuning. Fine tuning, cost intensive, more time consuming, easily can trace back. Yeah, in fine tuning also you can easily trace back. So let me write down: easily can trace back sources and fix problems. More memory consumption, generally better for most use cases. That holds true. So not preferred most of the times. And then the last point can be um, better accuracy and performance. Now this is something that I can guarantee. In fine tuning you will definitely have better accuracy and performance. Okay, so just repeating once again, whenever you get a problem statement, let's say a very simple problem statement is one of the problem statement that I solved in my previous company, was something related to AI based insurance claim processing. So in this case, the problem statement was insurance companies are, so insurance companies have some team, like let's say there is a team, okay, and in Hong Kong or in Singapore, most of the Asian Pacific market, what happens is, as the end customer, let's say I am working for a company, I'm just giving an example, let's say I'm working for Infosys, okay, and my medical provider is Bupa, my insurance provider. So Bupa will definitely give a handbook that is very specific to Infosys. So when the Infosys candidates or the Infosys employees, they go to Bupa, they will have to manually upload receipts and they apply for claim. Now this claim goes to this team, and this team has access to all of these handbooks and multiple other documents, and the team goes through documents, and then the team reverts back with a response whether it is approved or rejected. That was the use case. And we wanted to automate this process. So, which approach did I take? Definitely, as we are dealing with custom data, which is documents, handbooks, various other things, this is not solvable by just the pre-trained models, right? We definitely need either RAG or fine tuning. So, as a generative AI expert, what I did was I first tried with RAG, and then I used these handbooks and various other documents as my PDF, like my source data, and then I used the simple RAG approach. I chunked it down, I converted it into vector data and stored it into a vector database. Then we had a front end where the user is coming in and the user is uploading a bill. So immediately after uploading the bill, we had done some sort of a OCR technique to fetch all the bill details like name, dollars, money, and all those things. And then initial check was done. Initial check. If everything is good, then we were actually written down a prompt that behave as a expert in the field of insurance, take all this data, verify with this vector data, and see whether this claim is valid or not. For example, imagine the bill is related to let's say HIV, for an example, and let's say HIV is under general exclusions in this PDF document. That means Bupa does not have a coverage on sexually transmitted diseases. So in this case, what will happen? It will revert back that the claim is rejected. And all of this happens here in the prompt. So after you get this data from the vector data, I will just rub this off a little bit. This is where your data comes in. This is where your large language model sits, and then the large language model tells that this is rejected. So this was the flow. Now if RAG fails, then I would have definitely gone ahead with fine tuning. I would have used all of these documents on top of pre-trained model and train it again, change the parameters, and then use that final model here. So that is how you take decisions, and there will be certain scenarios or use cases where we will be going ahead and seeing how to fine tune different models. Hi, welcome back. Let's jump into fine tuning. What are the different attributes or different concepts that are related to fine tuning? And let's try to understand each one of them. So when it comes to fine tuning, I think everybody understands that the very first thing that we have is a pre-trained model, and that could be any of your large language models. And usually there is an instruct operation, right? And then let's say there is also a piece for safety. This is where domain knowledge comes into picture, or let's say you can consider this as a custom data. And let's say this could be something related to finance or banking, whatever use cases that you are doing. And now this becomes a fine-tuned model. And then eventually you are performing different tasks. Task 1, task 2, task 3, and so on. Let's try to understand what is full parameter fine tuning. We'll take an example to understand. Full parameter fine tuning. Just for simplicity, simply go to Ollama models. Oh, my bad. Ollama models. Now in this Ollama models, you will see tons of models. Let's say I'm just talking about the smallest one, which is Tiny Llama. So let's say we are talking about Tiny Llama. How many billion parameters does it have? 1.1 billion parameters. Okay, parameters. And model details are available. If you want to check model details, you will be able to get the architecture, Q4 underscore 0. This is something very important. We will be covering that very shortly. Okay. The quantization here is Q40. Okay. And various other things are there. Headcount KV, various other things. Even I don't know a lot of things. Context length is there, which is very important. So context length is 2048. Okay. What is context length? Context length means if you pass a prompt to your tiny llama and you are passing a huge input, let's say huge input, it will only consider the last 2048 tokens. That is the meaning of context length. Okay. What is quantization? What is this Q4 underscore 0? We will talk about it. First, try to understand the pain of fine tuning, full parameter fine tuning. Now, when it comes to full parameter fine tuning and considering tiny llama, if you want to update this entire model, 1.1 billion parameters basically means something like this. Let me just drag it this way. Eventually, this is nothing but a neural networks, right? So let's say you have a complex neural network dot 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 and something like this, right? You have different weights w1 dot 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 w, let's say 1 2 3 4 1 2 3 4 1 2 3 4, sorry, 1 2 3 4 1 2 3 4 1 2 3 4 12. So w12 and dot dot dot, right? Similarly, we have 1.1 billion weights in this particular neural network. Now, when you are doing a forward pass or a backward propagation in neural networks, in that process we update the weights, right? So when you are doing a fine tuning on this entire model, what is the problem? The problem is you are updating all the model weights. You are updating all the model weights and weights, that is all the parameters. Let me just make it like this. Got it? That is the problem, right? So which basically means a 1.1 billion model has 1.1 billion weights, or you can in simple terms 1.1 billion parameters, right? And so on, right? And I'm just taking an example of the simplest model. Imagine talking about llama 3.3 with a 70 billion model, 70 billion parameters. You can imagine, right? How much time will it take just for one epoch, just for one forward pass and a backward propagation, just for one epoch? It will take lots and lots of time, right? Because in this process all the weights are getting updated. So all the weights get updated repeatedly. Now I'm talking about an example. Let's say I'm talking about 5 epochs. So how many weights are updated? 5 multiplied with 1.1 billion, which is 5.5 billion. So imagine llama 3.3, which is a 70 billion parameter model, for 5 epochs. Total weights updated is equals to 70 billion multiplied with 5. I don't even know how much it will be. 350 billion. After billion, what do we have? I think trillion. So I think 0.35 trillion. Too much, right? So storing and updating these weights requires a lot of memory. Storing and updating these weights require, let me just drag it a little bit down, require a lot of memory, which limits fine tuning operation to larger GPUs. And this is one of the drawbacks. See, every pros has a con, right? One of the examples that I'll try to tell you a story. In one of my recent client work, there was a client called as TTI. So TTI is basically a company in Hong Kong. I mean, not the headquarters are not in Hong Kong, but yeah, as I'm working in Hong Kong, I was working closely with them. Now TTI wanted to do a sustainability chatbot. Sustainability chatbot. So they had a bunch of PDF documents, and they told me that we need to be good enough so that our chatbot understands all the jargons, acronyms, whatever you that we have in the PDF, and proper context. And if you look at the PDF, there are so many jargons related to ESG, related to sustainability, and it was very difficult for me to work with RAGs. But given a better model and a better EC2 instance, I would have definitely done the end-to-end work. But when I started working on it, they had given me a T3.2x large machine. For those who don't know, this is like I'm not 100% sure, but this was like a 32 GB storage and a 1 GB RAM machine. 1 GB or 8 GB? I think 8 GB RAM. 32 GB storage and 8 GB RAM. Now, in this configuration, I barely could use Tiny Llama. Even Tiny Llama, and I built this product based on RAG. I'm not even talking about fine tuning. I just did it using RAG, and I did the final delivery in Tiny Llama. Not sure whether that application is still up and running. Yeah, you can see this application is still up and running. By the time you check this, I don't think it will be available, and I will not recommend you to use this link. Just for demonstration purpose, I showed you. Could be my mistake as well. I should not show my client work, but just for the sake of understanding, I'm explaining this. So I did it on Tiny Llama. So 1.1 billion parameter model. The size of this was around 680 MB or something. So storage wise, it's completely fine. But RAM wise, it was taking up good amount of memory, like 1 or 2 GB memory it was taking. And to retrieve information on the chatbot, I was getting like 15 seconds delay. And that's because this model was taking 15 seconds. Now if you do the same thing with little bit higher version, I also tried on Llama 3.1, which was like a 2 billion parameter model, around 1.5 GB storage and around 3 to 4 GB of memory it will take. Now this took me like 30 seconds. So imagine, just with RAG I was facing all of these difficulties. If I would have gone for full parameter fine tuning, you can just imagine how much pain it would have been, right? So sometimes fine tuning looks really like a good approach. It might solve your business problem, but on the other hand, it can have a huge cost impact to your project. So as a Gen AI expert, you should actually take a step by step approach. Always try with RAG. Again, even in RAG, try with lower models, like smaller models. If you are able to achieve results in smaller models, why do you even need a bigger model, right? And then slowly go ahead with the bigger models, and then do a hit and trial, and then you will identify whether RAG is actually the solution or not. If you are not able to achieve anything, you have tried multiple models starting from 1 billion to 70 billion models, you are not able to achieve, then go ahead with fine tuning, else not. In the next video, I shall be talking more about how can we actually do the fine tuning, because this does not seem to be like a real option, full parameter fine tuning. There are some options like LoRA and QLoRA, which we will be studying in the next video. And using these techniques, these are both quantization techniques. Using these techniques, we will be able to do fine tuning in a better approach. Let's try to learn that in the next video. Hi, welcome back. In the previous video, we touched these topics, which is LoRA and QLoRA, and how are they different from the full parameter fine tuning process. So full parameter fine tuning is called as FPFT, but there is another concept called as PEFT. And what does that mean? This basically means parameter efficient fine tuning. Okay, and QLoRA and LoRA both are parameter efficient fine tuning processes. So LoRA is nothing but low rank adaptation. Okay, and QLoRA is nothing but quantized low rank adaptation. And these both are quantization techniques. Now you must be thinking, first of all, there was two jargons, and now there is another jargon which is quantization. What does that mean? Quantization simply means loading your model in a lower memory instance. So let's say you have a model. Imagine you have a 70 billion model. You want to load it in low memory instance, right? Imagine playing a high end graphics game on a lower, I would say, what do you say, like the I'm not getting the term, high end game in a low specification laptop. Let's say you have a laptop, manageable laptop. It's not like very high end laptop with lot of GPU and all those things, but you have just a manageable CPU, but you're still able to run that high graphics mode game in your laptop in lower resolution, right? This is exactly what is the meaning of quantization. You are basically breaking down the higher memory format into a lower memory format. So in simple terms, it's nothing but high memory to low memory. Low memory. Okay. So we have our large language models are nothing but neural networks, right? Let's say we have different weights, W1, W2, and dot dot dot. We have the final this thing. Now we already know weights are parameters, right? Weights are parameters. Now in general, larger model, more parameters, right? We have 70 billion model. So starting from the simplest model, we have 2 billion model, we have 7 billion model, we have 13 billion model, we have 20 billion model, we have 70 billion model. I don't know whether we have more than that or not. I am aware of 70 billion, not more than that. So the larger the model, the more parameters it will have, right? So large language model eventually have like billions of parameters, billions of parameters, and all of these parameters are usually represented by floating point values. Floating point values, all these parameters, all these weights. Okay, what is 1 byte? 1 byte is um, 1 bit is, sorry, 1 byte is 8 bit, right? Okay, 1 byte is 8 bit, right? Now imagine I'm talking about a 32 byte floating byte. If you divide, you will have 4 8-bit, or you can consider this as byte 1, byte 2, byte 3, and byte 4, right? Now let's take an example. Tiny llama. Tiny llama. How many parameters does tiny llama has? Let's say we have 1 billion parameters. 1 billion parameters multiplied with 4 byte, how many? It's going to be 4 billion bytes, right? And 1 gigabyte is how many bytes? Please take the help of Google. 1 GB 2 byte. What is the real number? 10 something something something. 1073741. 1073741 824. 824 bytes, right? So what will be the memory required? What will be the memory required to run this tiny llama? The memory required is 4 billion bytes, right? Divided by, let's say 1 GB is 1073741 bytes. So how many GB? 4 divided by 1.073, approximately 3.73 GB. This much memory is needed to run a tiny llama. So if you go back to this previous example, I told you, right? I was taking this example, right? So in fact, it was not 1 to 2 GB. In fact, it was 3 to 4 GB. My bad. Okay. Similarly, imagine this one will be even more than that, right? You can just imagine and multiply it with 2. So it should be like 7.4 GB, right? So to run tiny llama, you need 3.73 GB of memory. In fact, to store all the parameters. All params. So quantization, yeah, let it be like this. Let me just write down here. So quantization is the process of reducing the precision of numerical values, typically floating point values, representing the weights and possibly, um, one second. I lost some connection to my Miro board. Anyways, and possibly other parameters in the model to a lower bit representation. Simple. Quantization. Okay. So quantization is basically the process of reducing precision of numerical values, typically floating point values representing the weights and possibly other parameters in the model to a lower bit representation. Right? Now, for an example, let's say 32-bit floating point value can be represented as 4 bytes, byte 1, byte 2, byte 3, byte 4, right? This can also be represented as 16-bit, which will make it byte 1 and byte 2. And if you want to go further down, like to a 8-bit mode, this becomes 1 byte. Or you want to become even low, 4 byte. 4 byte can be 0.5 byte, or you can just simply write it down as 4 bits or 2 bit. 2 bits can be 2 bits, right? So this is your original one, right? This is your original. But if you want to go down into low resolution, low memory, you can go to 8 bit, 16 bit, 8 bit, 4 bit, or 2 bit. Okay. Now, talking about the difference of all of these things. right? What is the benefit? What is the benefit of quantization? The benefit is very simple. It reduces memory requirements and computation cost of running the models, right? So all the developers can use quantized models with lower memory and compute cost on edge devices or laptops without good GPU, right? So let's try to talk about the trade-offs. Let me just be back to my my black trade-offs. Okay, let's say I will draw a box here. So I will write it down here as precision type, memory usage, and performance trade-off. Okay. So let's say the first one is my original model. So this is nothing but full precision. Okay. The second one is nothing but FP16 with half precision. The third one is FP8, which is like a 8-bit integer. Then we have FP4. This is a 4-bit integer. Then we have FP2, which is a 2-bit integer. I should have done it in Excel sheet, but anyways, right? This is 100%, right? 100% or nothing but the default one, right? This is a 50% memory reduction. This is a 25% memory reduction. This is a 12.5% reduction. This is a 6.25% reduction. That means if this model takes 1 hour, this model will take 6.25% of 1 hour. You can just calculate. 6.25% of 1 hour will be less than 4 to 5 minutes, right? So how much is 6.25%? 6.25% of 1 hour, 3.75 minutes. So if this model takes 1 hour, this model takes 3.75 minutes. This model takes 30 minutes. This model takes 15 minutes. This model takes 7.5 minutes. This model takes 3 minutes, 3.75, or around 3 minutes 45 seconds, right? Something like that. What is the performance trade-off? Accuracy best, compute cost also very high, right? Accuracy is best, no doubt, but compute cost is very high. This one FP16 is nothing but a good balance between A and CC. In FP8 your accuracy goes down, and then obviously speed increases, right? Here accuracy is even down, speed is even better, and here accuracy is like very low, speed is very high. Now you must be thinking, why do we even use this? Because the accuracy is too low, right? But still, these kind of models are also applicable. Just think of some edge devices or IoT devices like smartwatches, where memory constraints and efficiency are basically, you can consider it as more critical than precision, right? So depends on use cases. It is always better to experiment. Many large language models are already available in quantized form. Now if you go to Tiny Llama, you can see Q4 underscore 0. What does that mean? That means it is a quantized version. I'll also tell you some of the jargons to remember the quantization. Okay, I will write it down as model names. Model name hints. Okay, integer 8, integer 4, integer 2. Integer 8, you can also call it as a Q8 model. Integer 4, you can call it as a Q4 model. This can be called as a Q2 model. Sometimes people also call it as GPTQ, AWQ and BNB, but major model names will be like this. So if you look at this one, this is like a quantized model. Now Q4 underscore 0, that means it's like a int4. Int4 basically means it's like a 12.5% memory usage reduction. So if I again go back to my client project, so originally it was around 3.73 GB, right? Memory usage. But that was for the 100% model. But as we are using like a 12.5% model, the memory usage will be 12.5% of 3.73, whatever it is. This much memory. Okay. So you can always do a hit and trial if you want to do practice on your own laptop or your own desktop. Whenever you are getting started with Olama models, you can always go to your task manager. You can check your memory and your CPU utilization. You will be able to identify, check the performance as well. You will be able to identify how much memory usage is happening and all those things. So Windows already provides all these task managers. If you are running your models on a Linux machine also, you can easily identify the memory usage by free minus h or df dot, like disk space. These kind of commands you can chat GPT to identify how much the usage is. You will be able to understand. So that brings us to an end to this particular video. Thank you. Hi. Let's try to deep dive into LoRA. What is LoRA? LoRA is low rank adaptation. Now, if I have to divide it, LoRA is consisting of two different parts. One being, let me just close it, one being the low rank part, and A basically means the adapters. Now, if I have to divide it into multiple phases, let's try to write it this way. The phase 1, we can focus more on what low rank is. Phase 2, we can look at what adapters are. And phase 3, we will look at the combination of LoRa and adapters. Now let's try to take example and try to understand more about the phase 1 part. Now what is phase 1? Phase 1 is all about low rank. What do you mean by a rank? So let's write it down. What is rank of a matrix? If you just don't know, in simple terms, rank of a matrix is nothing but the number of linearly independent rows or columns. So let's say we have a matrix. Let's say we have a 10 cross 10 matrix, right? How many linearly independent rows or columns do we have? Let's try to take an example to understand about the rank part. I'm taking an example where I will be focusing more on the columns part. Okay, so let's consider column for simplicity right now. Let's take an example. Example 1. Let's say I'm going to write it down. Let's say my numbers are 1, 2, 5, 3, 4. Let me write it properly. 3, 3, 9, 6, 9. 2, 3, 8, 5, 7. 4 1 6 5 9, just for simplicity. Now this is a 4 cross 5 matrix, right? So let me just draw it in a different color. How many columns do we have? Column 1, column 2, column 3, column 4 and column 5. And rows, there are 1 row, 2 row, 3 row and 4 rows. So there are 4 rows and 5 columns. Our task for this exercise is going to be identify the rank. Now going back to the basics, what is rank? Rank is nothing but the number of linearly independent rows or columns, right? Now let's first talk about, before getting into this matrix, what do you mean by linearly dependent or linearly independent? Now linearly dependent simply means, let's say I'm talking about few numbers, let's say 1, 2, 8. Let's say this is a list A, and there is another list which is 2, 4, 16, or there is another list which is 5, 7, 9, and let's say there is another list D, which is, let's say 1.4, 2.8, and let's say 1.4 times 8, 11.2. Now in this case, let's try to understand what is linearly dependent or not. List B is nothing but 2x of list A, right? So can I write it this way? List B is nothing but 2 multiplied with list A. I can. Can I write list C as something like this? No. So C is not linearly dependent. Talking about D, D is nothing but 1.4 times list of A, right? And that's why list D is also linearly dependent. So how many linearly independent lists do we have out of these 4? Eventually 1. Now let's talk about this particular matrix, okay? For simplicity, let me just copy this. Okay, I have copied. So let me just go a little bit down and we'll try to focus only on this example, right? Now, in this example, our target is to identify what is the rank. Now, and I'm just considering column by column. I'm not complicating it, not going into the rows part. Let's try to focus on columns. C1. For C1, do we have any previous column based on which C1 can be dependent or independent on? As C1 is the first column, C1 is purely independent by itself. Okay, so I'm just circling it because this is linearly independent. Now talking about C2, is C2 somehow linearly independent or dependent on the previous column? Now this element is like twice of this element, but this element and this element are same. This element and this element are like 1.5 times, and this element and this element are like reduced by 75%, right? Or reduced by, it's like 1/4, right? So C2 is also not dependent linearly. Now I'll talk about C3. Is C3 dependent on either C1 or C2 or both? Can I write C2 as, the first one is nothing but something like C1 plus 2C2? For first element, yes. For second element, 3 plus 2C2, which is 3 plus 6, 9, yes. C1, 2 plus 6, 8, yes. 4 plus 2, 6, yes. So this particular formula is valid. Sorry, this is not C2, this is C3. Okay. This formula is valid for C3, right? Okay, that means C3 is not linearly independent, rather it is dependent on both of these columns. So C3 is not linearly dependent. What about C4? Can we have a formula? Is C4 linearly dependent on either of these columns, C1, C2, C3, or maybe a combination of that? So if you look at C4, it's purely C1 plus C2, right? 3, 1 plus 2, 6, 3 plus 3, 5 is 2 plus 3, 5 is 4 plus 1. What about C5? So C4 is also no. What about C5? C5 is pretty much, it's like 2C1 plus C2. Now we can validate that. 4 is 2 plus 2, 4, 6 plus 3, 9, 4 plus 3, 7, 8 plus 1, 9. Yeah, this holds true, right? So either of these columns, C3, C4 and C5, are not linearly independent. They have a linear dependence on C1 and C2. Now here we have how many linearly independent columns? We have C1 and C2. So what will be the rank? The rank will be 2. So you can write rank as R. R is going to be 2. Now, so mathematically, I can write down these as C1 is dash C1 plus dash C2, C2 as dash C1 plus dash C2, C3 is dash C1 plus dash C2, C4 is dash C1 plus dash C2, C5 is dash C1 plus dash C2. So C1 is 1 C1 plus 0 C2, C2 is 0 C1 plus 1 C2, C3 is 1 C1 plus 2 C2, C4 is 1 1, and C5 is 2 1. That's my final equation. Moving on, the reason why I did this was, if I know this, if I know the linear dependence of all of these columns with respect to their previous columns, can I write it this way? This 4 cross 5 matrix can also be written down as, let me just write it, 1 2 3 3 2 3 4 1 multiplied with 1 0 1 1 2 0 1 2 1 1. If you look at closely, this is nothing but a 4 cross 2 matrix. This is a 2 cross 5 matrix. Now going back to very basic mathematics, when you are doing a matrix multiplication, let's say you are doing m cross k cross k cross n, this basically becomes m cross n, right? That's the basic fundamentals. So the output of this is going to be a 4 cross 5 matrix. So what I have done here is, this is nothing but my C1 and C2. These are nothing but my independent columns, and these are all of these numbers. The first row is 1 0 1 1 2, the second row is 1 0 1 2 1 1. Okay, now if you start doing the matrix multiplication, let me just quickly write down the formula of matrix multiplication. Is Cij is nothing but, let's say, summation of k is equals to 1 to m. I will write it down as Aik multiplied with Bkj. Now here A is my first matrix and B is my second matrix. Okay, that's my formula. Now let's try to go and try to solve this matrix multiplication. Not going to solve it for the entire thing, but let's try to solve it for row number 1. For row number 1, let's say my C11 is going to be, now this C, don't get confused with this C and that C, okay? Now this top C is for column. Now this C is basically coming from this formula. Now this is nothing but your new matrix. A is your matrix 1, B is your matrix 2, and C is your matrix 3, which is the multiplication of M1 cross M2, right? So in this matrix C, the first row and the first column, this is what the meaning of C11 is. It's nothing but this multiplied with this. So 1 multiplied with 1 plus 2 multiplied with 0, which is 1. C1, 2 is going to be this multiplied with this. 1 multiplied with 0, 2 multiplied with 1, which is 2. C13 is going to be 1 multiplied with 1, 2 multiplied with 2, which is going to be 5. C14 is going to be 1 multiplied with 1 plus 2 multiplied with 1, which is going to be 3. And C15 is going to be 1 multiplied with 2 plus 2 multiplied with 1, which is 2, 2, 4. 1, 2, 5, 3, 4. Going back to the first matrix. I'm just copying this here so that we are on the same page. Right? Do we have the first row? Yes? Do we have the first row? 1, 2, 5, 3, 4. Moving on. Moving on to row number 2. So C21 is nothing but this multiplied with this. 3 cross 1 is 3, 3 cross 0 is 0, which is 3. 2, 2 is 3 cross 0 is 0, plus 3 cross 1 is 3, which is 3. C23 is 3 cross 1 is 3, 3 cross 2 is 6, which is 9. C24, 3 cross 1 is 3, 3 cross 1 is 3, which is 6. 25, 3 cross 2 is 6, 3 cross 1 is 3, which is 9. 3, 3, 9, 6, 9. 3, 3, 9, 6, 9. Did we get this? Yes. Not going to do it for all the rows. I'm skipping row number 3. You can do that as part of your exercise. So let's say 4, 1, 4, 2, 4, 3, 4, 4, and 4, 5. 4, 1 is going to be nothing but just doing it in a different color so that it is visible to us properly. 4, this. 4 with 1 is 4 and then 0. So 4. 4 with 0 is 0. 1 with 1 is 1. So 1. 4 with 1 is 4 plus 2 is 6. 4 with 1 is 4 plus 1 is 5. And 4 plus 2, 4 multiplied with 2 is 8 plus 1, 9. So this is going to be 4, 1, 6, 5, 9. So eventually what I'm trying to say is this particular matrix, which was a 4 cross 5 matrix consisting of 5 different columns and 4 different rows, do not actually need information about all of these 3 columns. We are able to get this final output just by using C1 and C2, and that is because C1 and C2 are linearly independent. C3, C4, C5 somehow has a linear dependence with C1 and C2, right? So that's why we are able to write it this way. So going back, our initial matrix was something like this: 1, 2, 5, 3, 4, 3, 3, 9, 6, 9, 2, 3, 8, 5, 7, 4, 1, 6, 5, 9. Now this was a 4 cross 5. It we were able to write it like this, right? So the first two columns are this, which is a 4 cross 2, multiplied with 1 0 1 1 2 0 1 2 1 1, right? Which is 2 cross 5. So with respect to the rank, this becomes your rank. Understood? Clarity? Now, what is the advantage? The advantage is, if this is your original neural networks, if you do a full forward pass and a backward propagation, you are changing 20 parameters or 20 weights. But with simple changes with respect to low rank, you're able to get it with how many? 4 cross 8, 4 cross 2 is 8, and 2 cross 5 is 10. And the combination of them is going to be 18 parameters. And that is the example of parameter efficient fine tuning. You do not need to change all the 20 parameters. You can only change 18 parameters. And that is all about low rank. And this is just an example, right? I could have taken a difficult example, but it is difficult to understand. So I think this is clear to everybody. And 18 parameters, of course, is smaller than 20. That means we are storing less parameters, right? So generally speaking, the formula looks like this. W, which is D cross K, is nothing but A, which is D cross R, multiplied with B, which is R cross K. That becomes this matrix. Hi, welcome back. Let's move on to the next part, which is phase 2 adapters. Now, to begin talking about adapters, let me just give you a brief recap that usually there are three type of models, right? To get started with, let's have model 1, and then we have 2, and then we have 3, right? See, the difference between all of these three is very simple. The first one is nothing but a untrained model, right? It's not trained, so I'll just write it down as untrained model. The second model is trained with trillions and trillions of data, right? And this is nothing but a pre-trained model. I'm writing down as PT. And eventually, for your own custom data, here also we have input, here also we have output, here also we have input, and here also we have an output, right? And let's say you're training this on custom data, that becomes fine-tuned model. Now, what is the problem with a fine-tuned model? What are the cons of fine-tuned model? So if I start writing down the cons of fine-tuned model, just are time consuming and expensive process as LLMs get bigger. I'm not explicitly talking about LLMs, but in general, transformer models, right? As transformer models or LLM becomes bigger. The second is catastrophic forgetting issue. Apart from forgetting issue, we also have an overfitting problem as model forgets pre-trained objectives. Because when you are going to use an existing model, imagine a simple example, okay? I'm not talking about large language models. Let's try to talk about a very simple deep learning model example. Let's say I'm talking about Inception v4, right? Now, I'm not sure how many classes this model is trained on. Again, I'm taking an example. So try to understand the idea, right? Imagine Inception v4 is pre-trained with trillions of images and it has 1,000 classes, right? And if you are going to use this as one of your initial layers for your very specific use case, let's say you are trying to do some x-ray detection or something like that, or you are just analyzing, let's say, solar panel images for your use case. Some of the solar panels have cracks, some of them have no cracks. So you have two different use cases: solar panel with cracks and solar panel without cracks, right? Now this is a very typical use case, right? You have your own classes, and these classes might not be present inside this, right? That means when you're trying to use it as a pre-trained model and you're doing a fine tuning, that means you're updating all the weights, right? In that process there can be a scenario where the model might lose information. So there are scenarios where the model will start forgetting and will start overfitting. Could be a scenario, right? So let's say we need to fine tune a model. Let's say we'll take an example here with respect to natural language processing. Let's say we're going to talk about BERT. Okay, so everybody should know about BERT. BERT is nothing but bidirectional encoder only representation of transformers, right? And BERT has different variants. I'm just taking an example of, let's say, BERT large. Okay, now BERT large has 24 transformer blocks, right? And how does a BERT model looks like? If you have input coming in from here, let's say I'm going to draw something here, let's say, right? And let's say this is going to be my output, right? Now inside this, let's say I'm going to draw it in red blocks. This is one transformer block. Let me draw here another transformer block, dot 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 dot, another transformer layer here, right? So this is your block 1, block 2, and block 24. And what's inside these blocks? Let's say you have one, sorry, you have multiple blocks. Now this is, let's say, your I'll just talk about, let's say this is your multi-head attention, and let's say here is your feed forward layer, and then we have your layer normalization, and then you're passing the information. Okay, so let's say I'm just writing it down. The first one is nothing but your multi-head attention. Okay, the second one is basically your feed forward layers, and then the third one is basically your layer normalization. Okay, and if I have to point it out, this is this, this is this, and this is this, right? And the same architecture remains for rest of the blocks, right? These are the 24 blocks that we have now. And this is a very generic BERT large model, right? And BERT large model usually have around 345 million parameters. That means for the entire retraining with full parameters, you will be needing 344 million parameters weight changes, right? So without BERT, without PEFT, if you are doing a full parameter training, then you need definitely 345 million weights changes, right? In the entire forward pass and the backward propagation, right? So what is the problem here? What is the problem if we store or change 345 million parameters? Time consuming, memory consuming, and a lot of issues, right? Latency issues. So how can we perform a low rank adaptation here, or in simple terms, how can we perform adaptation, not adaptation, adaptation, right? How can we use adapters? Because this is what we're talking about in this scenario, right? This is the phase 2, and we need to talk about what adapters are. So BERT large model is basically of 345 million parameters, right? Now 345 million parameters basically means if you have your neural networks, let's say you have your input and you have your neural network, something like this, basically in your forward pass and your backward propagation, 345 million weights will be changed, right? And for this we need to store 345 million extra parameters for every forward pass or backward propagation, and that is where the adapters will come into picture. That is where PEFT will come into picture. We talked about PEFT, which is parameter efficient fine tuning, right? Now what exactly is parameter efficient fine tuning? I'm going to use the same BERT model but with adapters. And what does that mean? That means I'm going to do a very small change in this architecture. After multi-head attention and feed forward layers, I will quickly add a adapter. So I'm just rubbing this off. Here, as this is a new thing, I'm just writing down in, let's say, purple. So I'm going to add an adapter here, same adapter here, and same adapter here, right? So these are all nothing but my adapters, right? And adapters are added serially in all the transformer blocks, right? Now adapters helps adapt to a fine-tuned task. Okay, so taking an example, we have BERT, which is trained on multi let's say, what are BERT models trained on? BERT models are trained on, let's say, masked language modeling plus next sentence prediction, right? Now your BERT models is already trained on mask modeling, mask language modeling, and next sentence prediction. And imagine you want to do a very specific use case, you want to do something on sentiment analysis, and you want to train your own model, own data, and you want to do some parameter fine tuning, right? So here, as we are adding adapters, right, what's going to happen is only adapters weights are going to be updated. Your entire transformer block will not be updated, only the adapters weights. What does that mean? That basically means, let's say we want to do some fine tuning use case around sentiment analysis, and we have our new set of Q&A, right? And our new architecture will look like this, where we have adapters in all of these transformer blocks, right? Which basically also means that only adapter weights are going to be updated. Only adapter weights are updated, other weights are frozen. Okay, and it also means only a fraction of weights, not total 345 million weights, only a fraction of weights are going to be updated, and eventually it's going to be less memory consumption, less CPU utilization, and it's basically what we call as PEFT, and that's basically the adapter part. So we are clear on the low rank part and we are clear on the adapter part. Now let's try to combine, and let's try to also see what LoRa means, because LoRa is low rank adaptation. That means the combination of low rank and adapters. Now what I explained right now is just the functionality of adapters, right? we still need to understand what is the difference between this traditional adapters technique and LoRa in the next video. Hi, welcome back. In this video, we shall be focusing on the phase 3, which is LoRa, which is low rank adaptation. Now, we already have a fair amount of idea about what low ranks are. In short, when we are working on a matrix, let's say D cross K, we will be eventually be using, let's say, D cross R multiplied with B R cross K, and this is basically your rank, right? And what is a rank? It's already mentioned here, number of linearly independent rows or columns, right? And in the previous video, in the phase 2, we also talked about what adapters are, right? Adapters are nothing but introduced in, okay, before talking about that, quickly let me just show you what this is, right? This is nothing but your transformer block, right? For an example, you can treat it as a BERT 24 model, which is a BERT large model, right? Now this is your BERT 1, this is your BERT 2, dot dot dot, this is your BERT 24, and each of your transformer block has a multi-head attention, has a feed forward network or a layer, and then we have adapters. Now these adapters basically help you to cut down the number of parameters to a smaller parameters, right? And how does it do? Initially, BERT 24 is nothing but a 345 million parameter model, right? Without adapters, what happens is when you're going for a forward pass and a backward propagation, you need to update all of these weights. When you're introducing adapters, adapters have their own parameters. Let's say each adapter here is having like a 1 million parameters for an example, right? Let's say I'm talking about 1 million parameters. So how many total parameters do we have? We will be having 24 million parameters. And in this case, we don't have to train the full network or the full BERT 24 model. We just need to retrain, or we just need to use the adapter weights, and only the adapter weights will be trained. Now, what is the drawback of phase 2 when we are just using adapters versus low rank adapters? Low rank adapters is nothing but a combination of phase 1 and phase 2, right? With just adapters, we are still cutting down from 345 million to 24 million, which is completely fine. But low rank adaptation or low rank adapters further helps you to go down, right? The drawbacks of this process is adapters are good, but they are also having increasing latency and inference time, because adapters are basically added serially, right? Now let's try to combine both of our learnings that we understood in low rank and adapters. Let's try to understand what LoRa is. Okay, so let's say we are talking about BERT model, right? BERT large model is nothing but 345 million parameters, right? Now let's try to talk about 3 different scenarios, right? First will be without anything, without any adapters or without any low ranking technique. The total parameters are going to be 345, right? So let me just write it down here. Okay, before writing it down, let me just erase a little bit so that we have some space here. Okay, we have some space here. I'm just also deleting these things because these things we already know. And here, let me just write it down. Let's say we have 1 million parameters. It's going to be 1 million cross 24, which is 24 million parameters. Okay, now let's talk about 3 scenarios, right? Scenario 1. Scenario 1 is nothing but without adapters. Now without adapters, what's going to happen is total parameters is going to be 345 million, right? Now during back propagation, when you're doing a forward pass and a back propagation, all of your 345 million parameters are going to be updated. All 345 million parameters are updated. This means every weight in the model is adjusted based on the gradients calculated during the back propagation step. Okay, now talking about scenario 2. Scenario 2 is with adapters, with traditional adapters. Okay, with traditional adapters, what's going to happen is, instead of total parameters, I'm just going to write it down as adapter parameters, because here we don't care about how many total parameters do we have, because we just care about adapter parameters, because adapters are added to each of these transformer blocks, right? Now let's say we add an adapter module to each of the 24 transformer blocks, and let's say each adapter consists of let's say a couple of layers, right? A feed forward layer, for example. So let's say if each adapter has, for example, let's say 1 million parameters, each adapter has 1 million parameters. In that case, um, the total adapter parameters is going to be around, total adapter parameters are going to be around 24 million, with like 24 transformer blocks multiplied with 1 million, right? Now during back propagation, how many parameters are going to be updated? Only 24 million parameters of the adapters will be updated, while the original, the scenario 1 was having 345 million parameters, right? So obviously it's helpful. Now low rank adaptation is even better than this, or just change it to scenario 2, change it to scenario 3, right? Scenario 3 is with LoRA. LoRA is a combination of adapters plus low rank system. No, low rank basically means cutting down your original neural networks into a low rank neural networks, where we need to identify the number of linearly independent rows or columns, right? All the dependency will be removed, right? So let's say here I will write it down as low rank matrices. Now let's say instead of adding a full adapter, LoRa introduces two low rank matrices for each transformer blocks. Let's say, for example, LoRa introduces two low rank matrices in each transformer block, right? Now how many parameters we will have? So let's say parameter count, let's say, now again depends on the rank, right? For example, if we have a rank of 8, let's say, for the low rank matrices, let's say each matrix has dimensions that allow for efficient representation. The total parameters might look something like, I would say, let's say we have around 0.5 million parameters for each low rank matrices. Then the total LoRa parameters is going to be around, so it's going to be 0.5 million multiplied with the 24 blocks that we have. The total is going to be 12 million parameters. The total LoRa parameters or total updated parameters is going to be 12 million. Now during back propagation, only 12 million parameters of the adapters will be updated. Now imagine it to be a even low rank, not even 8, let's say 2 or 1. So the number of trainable parameters are even going to decrease from there. I hope you are able to understand, right? So if you talk about the summary, without adapters, we were having 345 million trainable parameters. With adapters, we have only 24 million parameters, and with LoRa, we have 12 million parameter updates, right? So the conclusion here is, using traditional adapters, we are able to significantly reduce the number of updated parameters. But LoRa takes it a step further by using the low rank approximations, resulting in even fewer parameters needing to be updated while still allowing the model to adapt effectively. This makes LoRa a very efficient method for the fine tuning technique. So, I hope you understood what LoRa means. Hi, welcome back. In this video, we will be talking about our next thing, which is QLoRA. We already know what LoRa is, which is low rank adapters. The Q part here is nothing but quantized. And what do you mean by quantization? I think we have already understood quantization in a separate video, that quantization is nothing but reducing the precision of numerical values, typically the floating point values representing the weights and possibly other parameters in the model to a lower bit representation, right? So let's say we are talking about a large language model. A large language model is usually trained on billions of parameters, right? I'm just writing it down as X billion parameters. For example, if you're talking about Tiny Llama has around 1.1 billion parameters. And all of these parameters are nothing but represented by floating point values, right? And when we drop it down to a lower precision, that means either to a 16-bit floating point. So by default, it's a 32-bit floating point, right? I hope everybody knows about this thing. If you break it down, you can either, so if I have to write it this way, 32-bit is eventually nothing but 4 bytes, and 1 byte is 8-bit, right? So 1 byte is nothing but 8 bits. So if you have to divide this 32 bits, you can either write 8 bits each, or you can just write down 1 byte, 1 byte, 1 byte, 1 byte, right? So if you have to break it down, you can either go to a 16-bit, which is nothing but 2 bytes, or you can go further down to 8 bits, or you can go to further down to 4 bits, or you go to further down 2 bits, right? So there are different quantization techniques, right? So eventually quantization is nothing but reducing the precision of numerical values. And if you remember, we have also gone through the different precision types, right? For example, talking about 32-bit. 32-bit is nothing but, you can consider it as FP32, right? Floating point 32, which is nothing but your 100% default model. Accuracy is best, computation power is very high, right? Computation cost is very high. 16-bit is nothing but a 50% reduced model. It's like a good model, good balance between the accuracy and speed. 8-bit is like a 25% model of the original one. Accuracy will be little bit lesser, but speed gain will be massive. 4-bit is again less accuracy, very fast, and 2-bit is insanely fast, but definitely very bad at accuracy. But nevertheless, these models also exist, especially in your IoT sensors or edge devices. So we use this, right? So that's basically quantization. If you don't know, please go back to the quantization videos and you should be able to understand what quantization is. Now coming back to QLoRA. What is the quantized LoRa? So we will try to go back to the previous screen where we had done different scenarios. I hope everybody remembers all of these scenarios. What we will be doing is we will be creating a scenario 4. Sorry, my bad. So we will be creating a scenario 4, which eventually is nothing but, well, let me just see, long press to unlock. Okay, let me just delete it and create it again. I think it's let's unlock. Okay. So the fourth scenario is with QLoRA. Now, what is the difference between, so we all know these three scenarios, right? What is the difference between LoRA and QLoRA? Let's try to understand that. Now, see, trainable parameters wise, there is not much of difference, right? In the original one, without the adapters, we were using a BERT as an example, BERT large model, where we were using 348 parameters, 345 million parameters, right? And similarly, we started talking about adapters. So with traditional adapters, we assumed that each adapter has 1 million parameters, and we were able to get 24 million trainable parameters. And in LoRA, assuming like a 0.5 million parameters with a rank of 8, we were able to achieve 12 million trainable parameters. Now, what is quantized LoRA? So quantized LoRA, or basically QLoRA, is nothing but an extension of LoRA that introduces the quantization technique to further enhance the efficiency in fine tuning of a particular model. Let's say in this example, we are taking the example of BERT large. So it will be even a better version of that model using the quantization technique. Now, parameters wise, nothing will change. Quantization basically refers to the reduction of the precision of the model weights, typically which is a 32-bit floating point, to a lower bit representation like 8-bit, 16-bit, 4-bit or 2 bits, right? Now this reduces memory usage and improves computational efficiency. So in QLoRA, both the original weights, the original model weights and the low rank matrices are quantized, right? So parameters wise, nothing really changes. In your traditional in your LoRa also, we were having 12 million parameters. In QLoRA also, we will be having same amount of parameters. So let me just write it down. Everything will remain the same. QLoRA introduces, okay, so it's same, it's just the same, it's the same 12 million parameters, but the weights are reduced precision, as simple as that, right? So that's basically the difference between LoRa and QLoRA. Apart from that, the core concept behind both are same. Both uses a combination of low rank and adaptation, but LoRa is on full precision. So when we were talking about the different precisions, right? Let me just go back to that particular table. If I have, yeah, this one. So in simple terms, this by default is LoRa. And if you use any of them, that's basically QLoRA. That's it. Trainable parameters, no impact. But within those parameters, QLoRA is a better version of LoRa, right? Because of the lower precision rate. That's it. The memory consumption is lower and accuracy is better. The performance is better. So that's all about QLoRA and LoRa.